Hello everyone, welcome back to Robot Programming Pro. Today, we're going to discuss how to make a robot go straight. You might be wondering, why is it not easy for a robot to move straight forward? Let me explain it simply. Our robot has two motors, and we can set the same power output for each of them. But in practice, the robot won't go straight as we expect. Why? Because most motors are not perfectly identical. Even small differences can cause one side to spin faster than the other, which makes the robot veer off course. Friction can also create this problem. For example, if one side of the robot is heavier, it presses harder against the ground. This increases the normal force, which increases the friction, slowing down that slide. Then how do we fix this with programming? It's easier than you think. If one side is always moving faster than the other, we just need to slow it down. We can detect the number and we can just subtract one side and add on to the other side with a constant. And we can let our real power to be the same, in which our robot is going straight now. But here's the problem. How do we know? How do we know what constant? Is it a 5? Is it a 4? Is it a 10? How do we know the exact number that we should put? Then, we need to know something first. Since distance equals speed times time, if the time is a constant, the distance directly shows us the speed. But here's the question. How do we adjust the power with the distance? We can just use a PID controller to calculate the fix. But there's another problem now. What is a PID controller? A PID controller is a type of closed-loop control system. This means that the robot constantly checks for errors, calculates corrections, and updates motor outputs in real time. In this case, the error is left motor distance minus right motor distance. By checking this error every loop, the robot can quickly react to the friction and ground differences. And there are three parts of PID. P, I, and D, which stands for proportional, integral, and derivative, which is a very advanced calculus problem. But in coding, we don't have to care about the calculus problem. We just use simple formula with arrow to calculate the fix in our computer. And we can start by, first, Kp, Ki, Kd are constants. You need to fine-tune these constants on your own robot. And the proportionals formula should be arrow times Kp, which is a proportional to arrow. And the I should be I arrow times Ki. And you'll be wondering what is Ki. It's just all the I arrow adding up. All the arrow adding up will create an I arrow. In code, we just have to write I arrow equals I arrow plus arrow, and which is getting bigger all the time. This helps fixing the long-term drift. And the third one is D. Our formula is D arrow times Kd. Now, D arrow should be arrow minus pre-arrow, and the pre-arrow should be arrow, but after updating D arrow, which means that pre-arrow should be the last times arrow, so it's called pre-arrow. And it's by calculating the difference between this and it smooths the control. And after all, we just have to plus P and plus I and plus D, mixing them together to create a fix. We can follow some easy steps to code. First, create a loop. Then, we can get the left and the right distance. Third, use a PID formula to calculate the fix. And then we just have to apply to the motors by left power equals power minus fix, and the right power should be power plus fix. Notice that one side subtracts the fix and the other side adds it. Do you know why? Share your thoughts in the comments below. And here's a simple example. We can use a very simple example, assuming that Kp equals 0.5, Ki and Kd equals 0. We're using just simple proportional for now, so we can keep it very simple to calculate by our manual hand. In loop 1, we see that left distance equals 100 and the right distance equals 95, which arrow equals 5. And the fix should be 2.5. And we just apply that to the motor's output. And we can see that in this time, the right output should be much larger than the left output because the right side is going slower than the left side. We just have to add a constant to it, which we can calculate the constant by using simple PID controller. And in the second loop, the left distance equals 150 and the right distance equals 147. Our arrow should be 3 and our fix is 1.5, which we can just regenerate an output. In the third loop, the left distance equals 200 and the right distance equals 199. Our arrow is getting smaller and smaller to 1. It's almost no arrow now, and our arrow fix is 0.5. And it creates our output almost the same. So now the robot is going perfectly straight, and that's what we wanted. So thanks for you to watch this video of Robot Programming Pro, and we'll see you in the next video.